and talk about each of our Big Bangs as a sub-universe. But very often people refer to each Big Bang as a universe, and then they use the term multiverse
yes.
for the whole thing. And
yes.
I think it's up to you what language you use. The multiverse idea has some very attractive features. I mean, it arose out of thinking of theories of inflation, but it has had interesting byproducts, because if this idea is correct, and we don't yet know, at this point it's just a speculation, but if this idea is correct, there's every reason to expect that in the different Big Bangs that occur, you will have different conditions, different values for what we call the fundamental constants. And so that the fact that the constants of nature are suitable for life, which is clearly true, we observe, may not be a universal fact. It may just be an accident, just as the fact that the temperature of the Earth is suitable for life is not true of planets in general.
Obviously, we have to be on a planet.
We have to be on a planet in which the temperature is suitable. I don't know exactly what the range is. Most people think water has to be liquid. We could argue about that.
Which doesn't leave very much range.
Perhaps life could arise in liquid methane, but clearly there are some limits. I don't think life can arise at 1 degree Kelvin. I don't think it can arise at 100,000 degrees Kelvin. So there's some range of temperatures in which life can arise. And it's only, as you say, it's only on the planets that happen to be in that fortunate position.
Or in the universes that happen to be.
And then this is then carried over by analogy into our universe, that it's only in those Big Bangs where the values of the constants are suitable where life can arise. In other words, if there was, I don't think there's really any evidence for a very precise fine-tuning of the constants of nature.
Well, that's interesting, because some physicists seem to think there is extremely fine-tuning.
I know, I've argued about that.
Yes.
One of the examples that is often quoted is a certain energy level of carbon, of the carbon nucleus. If it was 10% higher or 10% lower, then the nuclear reactions that build up oxygen from carbon and stars wouldn't work.
This was Fred Hoyle's argument, wasn't it?
Yeah, well, Fred Hoyle was the one who realized there had to be this energy level, and that nucleosynthesis wouldn't work well without it. Well, the fact that there is such an energy level, that just that energy does not require a fine-tuning of the, I think, and I've argued with people about this, I don't think it requires a fine-tuning of the constants of nature, because that state of the carbon nucleus is essentially a bound state of a beryllium-8, I'm getting very technical, a beryllium-8 nucleus and a helium nucleus, and that's just the condition that you need in order to allow nucleosynthesis to occur. So even if you change the constants of nature, the value of the energy of this state would change, but it would still be a bound state of beryllium-8 plus an alpha particle plus a helium nucleus. And so it wouldn't make much difference as far as nucleosynthesis. There is one constant that seems to be fantastically fine-tuned, but we don't, again, we're not sure, and that is the constant called the dark energy, or the vacuum energy, or the cosmological constant. This is the energy in space itself, not associated with any particles or radiation, but just an energy, so many calories per quart of space, everywhere in the universe, whether there's matter there or not. The amount of this has been measured. It's been observed that it's not zero. It has a small finite value. To give an idea of the value, it's about the amount of, in a volume the size of the Earth, whether the Earth is there or not, just in that volume of space, the amount of energy is the energy in a few hundred barrels of petroleum. Not a lot for a volume the size of the Earth. That energy is detected by its effect on the expansion of the universe. It's causing the expansion of the universe to accelerate, and that's something that was discovered 10 years ago by two different teams of astronomers studying the speed and distance of distant galaxies. Now we try to calculate what this energy is from first principles. There are various reasons why we can't calculate, but we can calculate certain contributions to it. For example, we can say fluctuations in the electromagnetic field, just due to the quantum nature of radiation, not down to arbitrarily small wavelengths, because we don't understand anything at very, very short distances, but just down to the shortest distances at which we think we understand physics, which is roughly 1/100th the size of an atomic nucleus. Those are the shortest distances that have been probed in our accelerators. So counting the fluctuations in the electromagnetic field, or the gravitational field, or any other field, down to the shortest distances that we have probed, the energy that we can calculate what energy that gives space, and it comes out to about 56 orders of magnitude larger than the observed value. That is a 1 with 56 zeros. Now, you just have to shrug your shoulders and say, well, there are the other contributions we can't calculate, like the contributions from fluctuations with even shorter wavelength. They clearly cancel.
But it's a pretty accurate cancellation.
It's a cancellation that's accurate to 56 decimal places.
Yes.
And that has us disturbed. And it's possible that that will be explained in a way that has nothing to do with the multiverse. It may be that for some fundamental physics reason that we don't know, the universe is evolving toward a state where that vacuum energy, that dark energy, is exactly zero. And it's small now just because the universe is old, and it's not far from that final state. No one has constructed a theory in which that's true. I mean, it's not only a speculation. The theory would be speculative, but we don't even have a theory in which that speculation is mathematically realized.
Yeah.
But it's a possibility. But the only other explanation, well, it's not even an explanation because we don't have a candidate theory, but the only explanation that seems to work is that this is just one of those things that varies from sub-universe to sub-universe, from Big Bang to Big Bang. In most of the Big Bangs, it's very large. It's much larger than what we observe. And in those Big Bangs, they go through, because this energy drives the expansion of the universe, depending on whether it's positive or negative, the universe either blows up so rapidly there's no time for galaxies or stars to form, or it crunches, it recollapses so rapidly, again, there's no time for life to form.
Yes.
So it has to be small for life to exist, and it's about as small as, in fact, that's interesting, it's not much smaller than it would have to be to allow life to arise.
And the fact that the cancellation is so precise means that the number of universes in the multiverse you need to postulate in order to anthropically be comfortable with it is very, very large.
And it must be at least 10 to the 56, or in fact,
exactly,
if you think you have some idea about fluctuations at even shorter distances, I think you would say at least 10 to the 120. In fact, that's a little disturbing, but a completely separate development, not motivated by this at all, has taken place recently in string theory. String theory, you know, is our best hope for a theory unifying all the forces of nature, gravity and all the other forces, all the particles. It's the most, it's been a little disappointing that it hasn't led to any specific breakthrough in understanding what we already know, but it's the best game in town, the best hope we have for a really fundamental understanding. It was realized a number of years ago, largely through the work of Edward Witten, that what had seemed to be about half a dozen different possible string theories was really only one string theory, that there's just one string theory, but it manifests itself in many ways